All right, so with this, I'm just going to go through some practice problems related to the Chapter 20 material. With each of them, I'm just going to leave the initial question up for just a little bit. So if you want a chance to work on them on your own, definitely just make sure you pause the video because I'm going to start going through the solutions pretty quickly. But with the first one, we're just given a generic reaction. We want to figure out based on the oxidation numbers for those two elements, A and B, which process is going to be oxidation, which one's going to be reduction, so we can identify which reaction we're going to have at the anode and the cathode. And then with the second one, we want to think about based on where we're having each of those reactions occur, which is going to have a higher potential energy. And then finally, we just want to think about if this is a spontaneous reaction, like it says, what that means about the sign of the cell potential. So we can't figure out the number specifically, but we can determine if it's going to be positive or negative. And with this, we'll see at the bottom here, these are going to be the two half reactions and the electrode that they're going to be occurring at. So with B, since it's going from 0 to +1, it's losing that electron. It's getting oxidized. That's going to be the anode, which means that the cathode, we're going to have reduction, where A is then going to gain that electron and then form a -1 charge. And then with this, we're going to see that the higher potential energy is going to be the one that gets reduced. So we're going to see that A be the half reaction involving A will be the case there. And then since this is a spontaneous process, we're going to see that the sign of the cell potential, so the E value, is going to be some positive number. That'll give us a negative delta G, a negative free energy change. So we'll see that either of those represent a spontaneous process. And then with the next one, we've got a diagram of a voltaic cell. And we're asked, based on the information there, to determine the reduction half reaction, do the same thing for the oxidation half reaction, and then determine the overall reaction from those two. And what we can see is we've got a zinc and a cobalt electrode. And as it says at the top, because we're not given information about either of the reduction potentials for those two metals, we're going to assume that the anode will be on the left-hand side with zinc. So that's going to be where we have oxidation taking place. So we know that zinc, if it's getting oxidized, only has one possible charge, going to be +2. So we'll see zinc goes from zinc to zinc 2. Cobalt is going to do just the opposite. So we'll see zinc is giving up 2 electrons, cobalt then gaining those 2. And then once we have the two half reactions, we can just add up everything on the left together. Same thing with everything on the right. And then whatever's the same on both sides is just going to cancel out. So that's why we can remove the 2 electrons. And we'll see cobalt 2+ along with zinc on the left. And then we'll just switch those charges on the right-hand side. So if we also wanted to label this diagram more, we could put the electrons going from zinc to cobalt, so we could have them moving left. And that means in the Sol bridge, we're going to see cations will move towards the cathode. If you think about it, we're having a negative charge go in this direction. So we're going to need to balance it out by having the positive move there. And then we're losing a negative from the anode. So we need negative ions. We need the anions to replenish that side. All right. And then with these next ones, like I said, just pause the video, give yourself a chance to kind of work through them on your own, because there's going to be 4 different reactions that we're going to balance with the half reaction method. And with each of them, I'm just going to kind of flip through a series of slides. It's going to show kind of a step-by-step process on how we kind of do that. But the first thing we need to do is identify the oxidation numbers for all of these substances, so we can identify what's being oxidized, identify what's being reduced, and split them into the 2 half reactions. So in this case, we'll see aluminum's getting oxidized 0 to +3. So it's increasing. That's going to be oxidation. It's losing electrons. And then the chlorine is doing the opposite. It's starting as +7 in the chlorate ion, but it's going to end up as -1 in just the chloride ion itself. And then with the oxidation half reaction, I just completed that one, just because that one's relatively straightforward in the sense that we don't have anything else in there. So the only thing we need to do to complete that one is just balance the charge. So since we have neutral aluminum on the left, we need a neutral charge on the right. So since we've got a positive 3 ion, we just need 3 electrons with it. But with the reduction piece now, we need to balance that oxygen. So we're going to have to place 4 water molecules on the right, which means we're going to need 8 hydrogen ions on the left to balance out the hydrogens that we added there. But once we do that, now we've got the reduction half reaction balanced in terms of the mass, but we don't have it balanced in terms of charge. We've got a positive 7 charge overall here, but a negative 1 on the right-hand side. So we're going to need to add electrons to the left. So we need to add 8 electrons there. And that kind of makes sense because if we think about the oxidation numbers again, plus 7 to negative 1. So chlorine's gaining 8 electrons. Exactly what we're showing in this half reaction now. But now that we have each of those half reactions, we need to be able to add them up. So whatever electrons chlorine's losing, or chlorine's gaining rather, aluminum has to be losing. But right now we're saying aluminum's losing 3, but chlorine's gaining 8 somehow. So we just need to make sure that those are equal. We're going to multiply by some factor. And in this case, the lowest common factor is just going to be 24. So we'll multiply the first reaction by 8. We'll triple the reduction half reaction, just so that each of them then have 24 electrons. But once we have that balance in terms of the electrons, we can just, again, add up everything on the left of both, add up everything on the right of both. And then once we do that, we just want to compare each side, see if there's anything the same. And with these ones, it's always going to be the electrons. So we've got 24 electrons, 24 electrons. Those are just going to cancel out. But we'll also want to check because in some cases we may have hydrogen or water or something else that's the same on both. But in this case, just the electrons, so we can see that's going to be our final chemical reaction. And then with the next one, we want to do the same thing. So we'll see zinc is getting oxidized 0 to +2, bromine getting reduced +5 to -1. And again, with the oxidation one, we can just add a couple electrons to the right-hand side to balance the charge. But with the reduction one, we're going to need to add 3 waters to the right. So we'll need to add 6 hydrogens to the left. And then again, that balances all of the mass. But we've got +5 charge on the left, -1 on the right. So we need 6 electrons on the left there. And then again, we need to balance both of these half reactions in terms of the amount of electrons involved. So we're going to triple everything on the oxidation half reaction and just have 3 of those zincs, 3 of the zinc ions, now 6 electrons in total in both. And then we can just, again, add up those 2 reactions, look to see what's the same. We're going to remove the electrons from both. And that'll be how we get our complete balance reaction. Then with these, you can always check just to make sure that you do have the complete reaction by looking to see if you conserve mass. So we've got 3 zincs on both, 6 hydrogens, 3 oxygens, and then just 1 bromine. And then in terms of charge, we've got +6, -1, so we've got a +5 on the left. We've got +6, -1, we've got a +5 on the right. So we can double check just by making sure that we conserve mass and conserve charge. And that's been the case here, so we can be certain that that's going to be our balanced chemical reaction. And then this will be the last one where we have acidic conditions. The next one will be basic conditions. So we'll have just one little extra sort of step that we need to consider. But this one's a little bit different in the sense that we've got oxygen on the left-hand side, but we've got it in 2 spots. And it's got 2 different oxidation numbers. So we can see it's going to be -2 in the dichromate ion. But then in peroxide, H2O2, hydrogen has to be +1. So in that case, the oxygen has to be -1 in order to balance it out. So peroxide is going to be one of the only cases where it's not -2 in a compound. The other ones being if it's with fluorine. But then on the right-hand side, we've just got elemental oxygen, which is going to be 0. So in this case, we've got oxygen being oxidized chromium being reduced because it's going +6 to +3. But we've got oxygen split in two cases, so it may be a little bit difficult to kind of recognize what we should be focused on. But what we're going to do is, since chromium's getting reduced and we've got the oxygens there, we're going to have to balance that with water. So we're going to see these oxygens aren't going to be oxidized or reduced. So when we're looking at the half reactions initially, when we're focused on this oxygen, that's going to be what's getting oxidized here. Because again, when we balance the reduction half reaction, we're going to have to add water molecules here. And it's going to go from -2 to -2 in the water molecules. So these aren't going to be oxidized or reduced. It's going to be the oxygen coming from peroxide that we're going to be focused on with the oxidation half reaction. But once we have those half reactions and the substances involved, we're going to have to balance oxygen. We're going to have to balance hydrogen. So in the first one, we've got, or the oxidation one, I should say, not the first one. But in the oxidation one, we've got oxygen balanced, but we need 2 hydrogens on the right-hand side. And then with the reduction one, we're going to need 2 chromiums on the right, but we're also going to need 7 water molecules. So then we have to go back to the left and add 14 hydrogen. But once we do that, now we've got each of those reactions balanced in terms of mass, but we've got to balance the charge. So we're going to need 2 electrons for the oxidation reaction. We're going to need 6 electrons for the reduction one. And then at that point, we need to make sure that the electrons are equal to one another. So we're going to triple that oxidation half reaction. And now we can just add everything up. But when we do it in this case, in addition to having electrons on both sides, now we're going to have hydrogen ions on both sides as well. So since we've got an imbalance there, so like with the electrons 6 and 6, we're just going to be able to completely remove them. But with the hydrogen ions, now we've got 14 and 6. So we're going to cancel out all 6 of these. We're going to cancel out 6 of the 14 we have on this side, but that's going to be why we're still left with 8 hydrogen ions on the reactant side of this chemical equation. And then with the next one, like I said, this is going to be in a basic solution. So we're still going to basically, let me just say basically, we're still going to follow those same steps. But when we add hydrogen ions in this case, since it's going to be in a basic solution, we're going to balance out those hydrogen ions by placing the same amount of hydroxide on both sides of the chemical equation. So if at some point we add, let's say, 4 hydrogen ions to the left of a half reaction, we're then going to add 4 hydroxide ions to both sides of that chemical, that half reaction. And again, in this one, we need to assign those oxidation numbers. So oxygen is going to be 0 in all of those substances, or not 0, -2 in all of those substances. But tellurium is going to go from 0 to +4. And then the nitrogen is going to go from +5 to +4. So we're going to see tellurium is getting oxidized, nitrogen is getting reduced. And then with these half reactions, we've got an excess amount of nitrogen on the right of the oxidation one. So we're going to need to add water there. Ooh, I might not have actually done this one in terms of acidic conditions. Okay, so then what we have here is actually for basic conditions. So we'll go back through and just fix this one in real time. But we get to this point, and that's going to be fine. But like I said, since this is in basic conditions, we're going to need to do that. So we're going to add the hydroxide, get rid of the subscript. And then since we added 6 water molecules, we're going to add 6 hydroxide to each side. And then we'll have to do the same thing here. So since we added 4 hydrogen there, we're going to need to add 4 hydroxide to both sides. Okay. But then when we do that, what we can do is then combine these into just water. So H2O. same thing up here. Whoops. Here we'll have 6 of them. So now we've got these two half reactions, and if we look at it, looks a little weird because we've got water on both sides. But if we look at it, they should be balanced. 2 nitrogens, 8 hydrogens, 4, 4, 8, and then we've got 4, 6, 10, 6, 10. So those are balanced. 6 hydrogens, 12, 12, 3, 9. Yep. Okay. So both of those are going to be balanced in terms of mass. But if we look at the charges, we've got a -6 here, and then just a -2 here. So we're going to need +4 electrons. Just to balance those charges, get -6 on each side. And then with the reduction one, we've got -2 here, but we've got a -4 here. So we're going to need 2 more electrons on this side. Okay. But now we've got an imbalance in those charges, so we're going to need to double the entire reduction reaction. So we want 4 electrons here. So when we do that, that means we'll get 8 water plus 4 nitrate ions plus 2 of the dinitrogen tetroxide plus 4 plus 8. Okay. And now we can do the full by just taking those 2 reactions and adding them up. With this one, we're going to have a little bit of work to do in terms of canceling stuff out here. So again, with it, we've added everything up. In this case, though, we just want to make sure we pay close attention to everything. So we can definitely remove the electrons from both, because we've got 4 of those on each side. But now with this one, if we look, we've got water in 2 places on the left, water in 2 places on the right. So we've got 8 plus 3 on the left, we've got 11 there. We've got 6 plus 4 on the right, so we've got 10. So what we're going to see is we'll still have 1 water molecule on the left-hand side, since we had 11 there versus just 10 on the right. And then with the hydroxide, we've got 8 and 6. So we can get rid of all 6 of those, which will cancel out 6 of these 8, leaving us with just 2 there. And then with it, that's all we can cancel. So let's double check this, and hopefully we got the correct answer. But if we just look at the charge, we've got -4 here, -4, so that's a good sign. Helium, just 1 of each, 4 nitrogen, 4 nitrogen, 2 hydrogen, 2 hydrogen. Then with the oxygen, we've got 12 plus a 13th. And then with the oxygen here, we've got 11, or 8 plus 3, giving us 11. And then a 12th and a 13th there. So that's going to be our full balanced chemical equation now. So with the rest of this stuff, just ignore for now, because that's going to be the acidic conditions rather than the basic. But this question comes from the textbook. Given a series of reduction half reactions, we want to determine based on that information which is the strongest and weakest in terms of oxidizing and reducing agents, and then which of these substances would be able to oxidize the C2 plus ion. And with it, we want to remember the more positive number is going to represent the, in terms of reduction half reactions, is going to represent the strongest oxidizing agent. And then just the reverse with the negative. So when we're looking at these ones, we're going to see the strongest oxidizing agent is going to be the most positive reduction potential. That's going to be A+. And then the weakest would just be the opposite, the most negative, so D3+. And then with the reducing agent, it's just going to be completely reversed. So D3 plus would be the strongest, A plus would be the weakest. And then with the final question here, which substance can oxidize C2 plus? So we want to think about which of these is going to have a more positive reduction potential. That'll be A plus, and then the B2 plus there. And then finally with the last one, this is more just a conceptual question, thinking about spontaneity as it applies to E and delta G. But we have a redox reaction that has a negative cell potential. So when we think about what that means for the sign of delta G, that means delta G is going to be positive. Remember, delta G is going to be equal to negative NFE. So N being the moles, F being Faraday's constant, E being the cell potential. So E and G have the opposite signs there. So if cell potential is negative, free energy change has to be positive. And that means this reaction is not going to be spontaneous, meaning it's going to be spontaneous in the reverse direction, meaning it's going to be as written, it's going to be a reactant favored reaction. So we're going to have a larger concentration of the reactants. If we think about our equilibrium constant product over reactant, we're going to see K is going to be a number less than 1 in that case. And then as I mentioned, this won't be a spontaneous reaction as written. So the forward reaction just wouldn't occur. It's just not going to be spontaneous. The reverse reaction could be, but not the forward reaction. And then with these ones, we just want to use the reduction potential table given, and then the chemical reactions given to determine the cell potential for each of these different cells. So in each case, we want to identify which substance is being reduced, which substance is being oxidized, so that with our our cell potential calculation, it's going to be the reduction potential at the cathode minus the reduction potential at the anode. So we need to identify which is which, just so that we have them in the correct order there. And with it, I underlined in the general equation, reduction at the cathode in red. So I'm just showing which substance in each case is being reduced. So we're going to take that reduction potential, plug that in first, and then subtract the reduction potential for the other half. And we're going to see in each case we'll wind up with a positive value, because these are all going to represent spontaneous reactions. But with the actual numbers, they're just coming from the table itself. So we just need to identify which is reduction, which is oxidation. And with it, you can even kind of just think about what we see here. Which of these reactions matches up exactly with what we have, versus if we look at the magnesium one, for instance, here we've got it +2 on the left to just magnesium. We see the opposite here. So we know this is going to be our oxidation piece, which is going to occur at the anode. So we're going to plug in that value second. But with each of them, again, we see a positive number just because that's going to represent spontaneity. And then I think this is the final one, but we're given a reaction. We're given the half, or we're given the reduction potentials for each of those half reactions involved. And we want to determine the cell potential, the equilibrium constant, and the free energy change. But the way we're actually going to want to do this is first get the cell potential, then we can get the free energy change, then we can get the equilibrium constant. And with the first piece there, getting the cell potential, it's going to be the same as we just had on the previous slide. What we're going to see is the manganese is going to be getting reduced. So that'll be our first piece of the equation minus the 2.77. So we're going to see ultimately we have a cell potential of 1.69 volts. And then with the free energy piece solving for delta G, remember we've got this equation negative NFE, so N being the moles of electrons involved. So in this case, losing 2 electrons, gaining 2 electrons, times Faraday's constant, 96485 coulombs per mole, and then just times the standard cell potential, which we just solved for 1.69. So doing all that, we're going to get a free energy change of negative 326,000 joules per mole, or negative 326 kilojoules per mole. But when we go to solve for K, it's going to be important that we pay attention to those units, because with the K, we can use the free energy equation itself, Remember, at equilibrium, delta G here is just going to be equal to 0. So we can eliminate that term and then separate the rest of this out. So just subtract RT, ln, Q. And that's why we get a negative sign here. It's because we subtracted this to get it by itself. But at equilibrium, Q is going to be equal to K. So we can just substitute K in and then solve for that one. So we just have the negative delta, or we have the free energy change from up here. I really should have a degree symbol next to these delta G's as well as that delta, or that E value. But we can plug that value in. R is just a constant, and that's why I'm saying we need to pay attention to units. If we have 8.314 joules per mole Kelvin, we need this value to be in joules. We could convert this to 0.008314 kilojoules and then have kilojoules here, but we just need to make sure that those units match. That's why we also need the temperature to be in Kelvin for these ones. And then the final piece, ln K. So once we kind of multiply these together, divide both sides by that value, we'll get 131.6 is equal to the natural log of the equilibrium constant. So then we can just use E to get rid of the natural log, and we'll see K is going to have a very, very large value, 1.42 times 10 to the 57. So this is going to be a product favor reaction by a lot. We're going to push this reaction essentially entirely to the right-hand side.